think next up we have Minmin. You want to share your slides?
Yeah. Can I see it?
Yep.
Okay.
Okay.
Sorry. Yeah, that's right.
So to end the day, we have Minmin Wang from the University of Sussex, and she's going to be talking about branching process-inspired numerical approaches to the neutron transport equation. Thank you.
Okay. Thank you very much, Emma. So my talk we sort of carry on where Emma left this morning. Well, let me first start with a very quick recap on Emma's talks. So the main object is the neutron transport equation that you've seen several times today. So this describes the evolution of the neutron flux inside a nuclear reactor core. So a bit more precisely, I'll write to psi T of RV to be this neutron flux. So here R is just a position inside a 3D domain. A 3D domain where the nuclear reactor occupies, and V takes value in this capital V, just representing the set of possible velocities. So this quantity, psi T of RV, is a neutron flux at time T emitted from the initial configuration RV. So put another way, here we are tracking the neutrons according to their departing points. So for this reason, the equation here is sometimes also referred to as the backward neutron transport equation, as opposed to the forward equation that we've seen in Emma's talk. Okay, so this equation tells us that the change of the neutron flux in time is due to three factors. So the first term is a transport term, basically just saying the neutrons travels at the constant velocity v if it's left undisturbed. Then there's a second term, which is a scattering term. So it says that the neutron, what can happen to the neutron is at some rate, this rate sigma s, it could switch to a new velocity, and this new velocity is picked up with the probability according to this this density function, okay, pious. And then the third term is a fission term, which is essentially a branching event. So what happens is at this rate sigma f, one neutron could be replaced by some number of the neutrons. Okay, and this event is kind of characterized by this function pi f here. So in particular, if you look at the total mass of this function, right? So this is not a probability density function; it's a density function for a finite matter. So this total mass gives you the number, the mean number of the new neutrons. And then each of these neutrons can have a new velocity. So again, picked with some probability proportionate to the function pi f. Okay, so this is what happens inside the nuclear reactor and what happens about at the boundary. So at the boundary, when the neutron leaves, you get killed immediately. So this explains this boundary condition. Okay, so here NR is the outward facing normal vector. Okay, so together with the previous PDE, so this gives the system of the neutron transport equation. So here we are primarily interested in the solution to the neutron transport equation with a given initial condition. So let G be this initial condition. So from time to time, when I want to emphasize on the dependency of the solution on this initial condition, I will write a precise T of G, okay, so to be the solution, to be this solution. So you've seen in Emma's talk that under rather mild conditions, the neutron transport operator has a lead eigenvalue. So put another way, this is saying that the neutron flux has a growth rate. Okay, so meaning that this function beside t can be approximated when t is large by this exponential function. So e to the power lambda star t, and here this lambda star is precisely the lead eigenvalue of the neutron transport operator. Now, depending on the sign of this lambda star, you can have 3 different scenarios. So in the first case, which is a supercritical case, we call, your neutron flux grows exponentially fast. In the so-called critical case, your neutron flux sort of stabilizes over time. Okay, and then there's a subcritical case where the flux reduces to 0 very quickly. So our aim here is to estimate the value of this lambda star by solving the neutron transport equation using some Monte-Carlo method. Okay, and we're going to see 3 approaches, so 3 algorithms. So all 3 of them follow very naturally on from what Emma talked about this morning. So there's the neutron branching process, which is basically just a branching particle system. Then there's the many-to-one formula, which leads to the so-called basic neutron random walk. And finally, combining this with the 2-H transform, we'll get to this the so-called H neutron random walk. Okay, so I'll talk these algorithms in more details. And then using some sort of well-known tools on branching animations, we can also carry out analysis on the accuracy and complexity of each of these algorithms. All right, so this is a plan. Okay, so here we go. So let's start with the neutron branching process. Okay, so so as I said, this is a branching particle system. Okay, let's say we start with 1 particle at the configuration RV. Okay, so if you recall the interpretations of the coefficients in the neutron transport equation, so what happens below should appear very natural. Okay, so imagine you're neutron. What we do is, so you start from this this given configuration RV, and then you travel with this constant speed v in straight line. Okay, if you leave the domain, you're dead. And if you're inside the domain, okay, you may change your velocity at some random time, which is distributed according to some exponential random variables, where the rate is given by this function sigma s. Okay. And when that event happens, you're going to pick up a new velocity v prime with this probability density here. Okay, so say now you have a new velocity, so you carry on your trajectory with this new velocity. And another thing that can happen to you is at this rate, sigma f, okay, you're going to be replaced by a random number of new particles. Let's say this number is n, and each of these new particles, they're going to occupy the same physical position as you do, but they can acquire some new velocities. Okay. So the joint distribution of this variable n and the new velocities is captured by this distribution curly E, which may depend on where the branching occurs. Okay, and this distribution curly E so satisfy this first moment relationship. Okay, as Andy remarked, this is not enough to characterize the whole distribution. So in terms of implementation, we do have a little bit freedom on choosing what this E is exactly. All right, so let's say all these have been picked. So each new particles have a new velocity. And what they would do is just evolve independently in exactly the same way as you do. Okay, so this is a definition of the neutron branching process. What's the connection with the neutron transport equation? So it turns out that mean behavior of the neutron branching process verifies the NT. Okay, so more precisely, let me write NT to be the number of the particles or neutrons which are still alive at time t in the system. And let's say RIVI are their configurations. So I'm going to put a unit mass at each of these configurations. And this gives me the empirical matter of the system at time t. Okay, so I'll write xt for this empirical matter. So this gives me a random point matter. I'll take the function g, integrate g with respect to this random matter, take the expectation, and turns out this corresponds to exactly the solution to the neutron transport equation with the initial condition g. Okay. So this relationship leads to very naturally the first algorithms that I call the neutron branching process. Okay, so what we do is the following: we simulate this neutron branching process, starting, let's say, from a single particle at a given configuration R&D. Okay? And so in practical terms, the simulations involves mainly sampling a lot of exponential random variables. So in a way, it's straightforward to do. And you can even have a bit fun with the geometry. Okay, so for example, also we have two examples here on the right-hand side. So in the first example, we have a cubic reactor, and inside it, there are two spheres indicating kind of the source of fuse. So this is where the branching occurs. Okay? And outside of these spheres, this is basically just void. Okay? And in the second example, so you have these rods which give which are where the branching occurs. All right, so simulate such a system and up to time t, and the output will be the empirical matter of this system at this time t. Okay, so I denote it as xt. And then repeat the simulation for k times. Record the output from each of these simulations. Take the average of these k outputs. Thanks to law of large numbers, this will give us a good approximation of its expectation, which with things that correspond to exactly the solution to the NT. Okay, so this leads to very naturally the first estimator for the eigenvalue. I'll call this the MBP estimator. So this estimator is just given by taking the average and then raise it to the power 1/t, sorry. Okay. So we can ask how quickly this estimator converges to the true value. Okay. So it turns out this convergence rate will depend on the criticality of the system. So in the supercritical system, the rate is the best. Okay. So this kind of show in the picture here. So in the picture on the left-hand side. So this is a supercritical case, and the worst scenario happens in the subcritical case, which is kind of not surprising because in that case, your system dies out very quickly. Okay, and this sort of backed up by the simulation as well. So in this example, which is a subcritical, you see the orange lines that correspond to the evolution of the estimator over time. So there's a lot of wobble towards the end. All right. So I'm just going to say a few words on how these bands come, where these bands come from. Okay, so we want to bound this mean squared error. Very naturally, you want to insert the solution psi TRV into this equation, and then use some sort of triangular inequality. So this leads us to these two terms. So the second terms will give us this this 1 over t squared term, which is common in all three cases. And the first term, if you forget about the 1 over t exponent, this just boils down to looking at the second moment of the empirical measure. Okay, so this can be obtained by the Minmin-Wang formula, which again Emma had already touched upon. Okay, so from that, very quickly you can get an estimate on the variance of this empirical measure, which have different rates in depending on the values of the lambda star. Okay, so this is the convergence rate. So I said we also want to look at kind of the complexity of the algorithm. So for us, this translates to the question that how much a simulation of the NDP costs. Right? So if you look a bit more carefully at the algorithm, so we see there are kind of two aspects of the cost. There's the memory cost, which consists in storing the trajectory of each particles. And then there's also the sort of CPU time cost, where you're doing a lot of samplings of the scattering and fission events. Okay, so basically this means that we need a counter for all these kind of events. Okay, so let's devise such a counter. Okay. So the idea here is we want to count, let's say, the trajectory to number of particles which are born before a certain time. So what we do is looking at all the particles which are ever alive in the system. And let's say U is just such a particle. We denote by BU the birth time of this particle. Okay, so if we sum over all U, where the birth time is less than t, so we get to the number of particles which have been alive up to time t. Okay, so the first term in this formula should just so takes care of counting these events. Actually, you can do a bit more, can do a bit little fancy counting. So you might want to put different weights depending on where the particles are born, perhaps some locations especially. That's why we introduce this function g, which is just a generative function. By choosing g differently, you can put different weightings on the particles. Okay, so that's the first term in this cost function, and then you want to count on the number of the scattering events. Okay, so that corresponds to the second term. Okay, so again, you're going to sum over all the particles, and then let's say for a particle u, you let SUI to be the sequence of its scattering times. Okay, and then if you count over all these times which have happened before time t. This gives you the number of scattering times in the system which have happened before this time. Okay, so again, you can do a little bit of weighting by putting a function f here. Okay, so that's why we have chosen this function and as a kind of estimation for the cost of the simulation up to time t. So of course, if you take some simple examples and put constant functions, let's say f equals 0 and g equals 1, then this will give you some rough estimate for the memory cost. And if you put both of them to be 1, this gives you some estimate on the CPU time. Okay, so that's the cost function. And we want to know how this cost function increases over time. Okay. Now, if you look at the neutron branching process, you realize that the scattering events and fission events, so they arrive according to some inhomogeneous Poisson point processes. Okay, so therefore, just using some standard tools on the point process, and it's not difficult to derive their rate, the growth rate. So for example, you can looking at their expectations, and turns out the expectations again grows in different weights, different rates depending on the criticality of the system. So here the supercritical system has the largest cost, which is again reasonable. And if you're simulating a subcritical system, because it dies out in finite time, the cost will just stop at a certain level. Okay, so up to now we have an estimate on the convergence rate on one hand, and the estimate on the cost on the other hand. So it seems natural that you want to kind of balance these two things. Okay, so one of the games we have played with these two estimates is to look at a given level of accuracy. Say I want the mean square errors to be less than 1%, and then using these two estimates to kind of determine the optimal values for the number of simulations k and the time horizon t for these simulations to sort of minimize the total computation in cost. Okay, so this is one of the games you can do, but there are all other sorts of optimizations you might want to do as well. Okay, so that's so much for the neutron branching process. Now let's move on to the neutron random walk, which is a result from the many to one formula. Okay, so let me just explain very quickly what the idea is. So let's recall the neutron transport equation, which tells you the evolution of precise t by three external forces. So here, what we want to do is kind of rearranging these three terms into two groups. The first is sort of a branching terms, and second, the rest will correspond to some motion. Okay, let's start with the branching here, the beta. So this is the fairly straightforward. So what you do is looking at the main number of new particles. Okay, subtract 1, which is the old particle just die out. Okay, so this gives you sort of the net gain from the branching event. Okay, so this determines the first coefficient in this many to one formula, which I denote as beta, and then you put all the rest into this operator L. And turns out this operator L has an interesting interpretation. So this corresponds to the motion of the falling particle. So this is a particle which, let's say, starts from RV, will move a straight line with this constant velocity v until one of the things happens, either it leaves domain and get killed, or it will change velocities at some accelerated rate alpha. So it takes so this alpha is a combination from the scattering event as well as the fission event. Okay, and then when this thing happens, it will pick a new velocity with a new probability pi, which again is a combination of the fission and the scattering event. Okay, so I'll call the distribution, the law of this particle as a neutron random walk. Okay, so once you have such a neutron random walk, what you can do is check if it is still alive at time t. If it is, then fit this into this function g, then amplify it by this exponential weight, take the expectation, and turns out this gives you another representation of the solution to the MD. Okay, so this is what we call the magnitude 1 formula. So this formula very naturally leads to our second algorithm. Okay, so this gives us another estimator for the lead eigenvalue, which is done by simulating k-independent neutron random walks. Okay, and then check if they are still alive at time t, and then take the average of this quantity raised to the power 1/t. Okay, so at first sight, you would say in doing this, we have scrapped the diffusion. So this might improve on the efficiency of the algorithm. But turns out there are problems with the numerical aspect of this estimator. So sort of as you can see from these two plots here, so the orange line corresponds to the branching system we talked about before, and then the green line corresponds to the estimator obtained from this neutron random walk. Okay, so so there's a lot of fluctuations in the green lines. So one reason for the poor performance of the neutron random walk estimator is because of this indicator. All right, so the probability of survival up to time t is an exponentially small event. Okay, so you may start with a very large number of simulations, but you might end up with only a handful of particles which are still live at time t, or even none at all. And clearly, this will be very bad numerically. Okay, so this kind of problem with this neutron random walk, but all is not lost. We build on this neutron random walk idea, but this time we try to improve on the survival probabilities by using this Dooh transform idea. Okay, so let me explain this very quickly. So let me write L for the infinitesimal generator of this neutron random walk that we've seen in the previous slide. And then, so it turns out this quantity here is a martingale. Okay, so once we have a martingale, we can use it to perform a change of matter. So I'll denote pH, this new probability under this change of matter. Okay, so you can think of it as some sort of biasing, but it turns out this pH has a very neat interpretation in terms of a neutron random walk. So you take your old neutron random walk, and it sort of has a new life under this new probability pH. So with that, what it does is the motion is pretty similar. It goes straight lines with a constant velocity, but now it has a new scattering rate. Okay, so this new scattering rate alpha h is given by this formula here. So I should have mentioned, so here h is generic function, which is positive and bounded. Okay. So in particular, because h appears in the denominator here, okay, with h. So if you let h goes to 0 at the boundary, so it means the scattering rate alpha h will diverge to infinity at the boundary. So the particle will almost surely turn around before hitting the boundary. Okay? So this ensures the particle will never leave the domain under this new probability. Okay. So this gives us the third estimator for the eigenvalue. Okay, so combining the magnitude 1 and the change of matter. Okay, so this gives us the formula for this H random walk estimator. Okay, and then you can note that here we no longer has this indicator of survival up to time t, because we can, by choosing H smartly, we can ensure this happens all the time. Okay, so we can also estimate the convergence rate of this estimator, as well as the cost function for the a similar cost function for the implementation for the algorithm. So it turns out this is related to some new exponent lambda h and lambda h prime here. So both of them depend on your choice of function h. Okay, so their values are not known except in very exceptional cases. One of these cases where you take h to be the lead eigenvalue. Okay, the lead eigenfunction phi. So in that case, the convergence rate or the mean squared error, okay, has this rate. So if you recall, this actually corresponds to the rate in the supercritical case of the neutron branching process. And then the cost function is just a constant function, just where it goes converges to a constant. Okay, so in both cases you have the Bath rates, and so the convergence rates correspond to the quickest rate of the branching process, and the cost is relatively few. So in some sense, this you can say having the Bath of 2 volts. But of course, the problem is in reality, we don't know how this eigenfunction looks like. Okay, so what we can do is starting with kind of an educated guess of this eigenfunction. Okay, so I'll just show you sort of one example. So this is a very simple example. This is a toy model over toy model. We have looked at a 1D nuclear reactor, which is just an interval. So it turns out in this case that the NT has analytic solutions. Okay, so then we can find out the explicit expression for the eigenfunction, which is plotted in the red line here. So we have taken 2 approximations for this eigenfunction. One is linear by the purple line, and then there's a quadratic approximation which is depicted in the green line. So you can see that the green line, so the quadratic approximation is a very good approximation of the 2 eigenfunctions. But it turns out that the linear approximation is already good enough. Okay, so in this plots, so the linear one, which is again in the purple line, and the green line correspond to the quadratic lines. So both of them have outperform the branching process estimators. So that's why so we have in our paper proposed to just start with a linear approximation to plug into this H transform thing. So you want a linear function which is 0 at the boundary, okay, and then just this will be something you can start with, and then you can kind of improve on your guess of the H function by running some simulations. Okay, this Emma have talked about as well. So you look at the simulations, and there's some way to get more and more information on what this eigenfunction looks like. Okay, so I think I'll wrap up here. So so just using some tools from the branching particle system. So we have seen some Monte algorithm, and as well as estimate their convergence rate and complexity. So I think I'll stop here.
Thank you very much, Minmin. We have a few minutes for some questions if anyone has any. Okay, so I'll start. So how kind of complicated could it be? Is it sort of practical to take the H function? I mean, because of course, in some sense, the more you can say about the function H, the better, but then for simulations, it can be quite complicated to simulate, right? So have you looked at like a payoff between these two in more detail? Like, of course, you have the linear and quadratic, but
so yeah, I mean, even the linear quadratic, we kind of restrict to the 1D case, right? So in the 2D case, I think we just did the linear approximation as far as I remember. Well, I mean, it's possible to do the kind of the quadratic, but the impression we have is perhaps linear is already not bad thing to begin with, perhaps.
Okay.
So as long as you make it to be 0 on the boundary, so that already will make sure the particles will never leave the domain, and that's already a big gain in terms of the kind of efficiency of the algorithm.
Okay.
But yeah, definitely there's something we can look at in the future.
Okay. And you mentioned the many to two. Have you tried to simulate this as a kind of payoff between a many to one and full branching system? Is there some gain in trying to do this, or even a many to few?
I haven't thought about that way. So yeah, I mentioned many to two, but it was really just a tool for us to estimate the variance of the estimator. I haven't thought about this in terms of the algorithm. No, I don't know. Yeah, perhaps can do that. Yeah.
Okay. Are there any other questions from anyone in the audience? No. Okay. So could I ask everyone to unmute themselves and just thank the two speakers from the final session to date, please? And I think that's it for today. Alex, did you want to say anything? Or?
Not really. I think it's tomorrow at 9 o'clock UK time. I think I'm talking, and then there'll be a discussion session tomorrow at 10:30.
Okay.
I think the next. I hope I've got that right.
I think so, yeah.